All right, so so today I want to talk about some, let's say, some various results on critical points of Laplace eigenfunctions. And the idea is that when you look at eigenfunctions, broadly speaking, the eigenvalue tells you how much a function oscillates over the whole manifold. So basically, the higher the eigenvalue, the more it should oscillate, the more, let's say, you should have more oscillations, meaning more critical points. You should have more maximum, more minimum. If you look, for example, into the irrational rectangle, you have this grid, and then you have no multiplicity as well. So you can safely say that the number of critical points goes up with the eigenvalue. But it is sort of a tricky subject because critical points are very, very specific. So we'll dive into it today in sort of a very lighthearted manner. So the thing about it is most of the results that I'm going to give today are counterexamples, and they involve some funny ideas. So we're going to start by just putting the setting, and then we'll forget it later on. So you have MG, n-dimensional Riemannian manifold. We ask usually for M to be smooth. We will also review some cases where M is analytic, but we'll get up to that later on. So we take negative, actually we take negative Laplacians. We have positive eigenvalues. We have a sequence of eigenfunctions. And then we look at critical points as the point where the gradient vanishes. So quite simple stuff. And the main idea today is that we want to count critical points. Now, we hit a little snag early on. If you look at just the two torus, eigenfunctions are just sines and cosines. So if you take just the square torus and then you look at it in R2 as the square with the side identified, when you take sine of x, what you have is that the critical points are kind of like these vertical lines. So essentially, if you want to count the points, you have infinitely many of them. So, so today we're going to focus more or less on isolated critical points, just because the idea of counting a critical strip is a little bit vacuous in itself, and I don't want to get into homology and then counting connected components and stuff like that, especially early on. So we're going to consider mostly isolated critical points. So why study critical points? I said that when you look at the eigenvalue, tells you in a broad way where the eigenfunction oscillates. So does it have scarring where it oscillates and it goes up really high? Does it have a part of the manifold where the eigenfunction will sort of crunch in itself? All these ideas are sort of understood in terms of the eigenvalue, but locally it's a little bit harder. So critical points tell us that you have this sort of local oscillation of eigenfunctions, but it doesn't tell you much more than that, except there is one sort of rigid idea about critical points is that when you're in dimension 2, you have a smooth manifold, and then you have a point on the nodal set. It's an old theorem by Lippmann-Beers. I think it's in the 50s, if I'm correct, that says that all the nodal lines must cross at equal angles. So if you have 2, it's like this. If you have 3, it's kind of like an hexagon. So this is sort of like the more rigid property of critical points. But really, when you're not critical points on the nodal set, you have a lot of flexibility. Sorry, this is terrible timing, and just give me 1 minute. Sorry for that, mail delivery. All right, so where was I? Yes, so if you're not on the nodal set, critical points a priori can be anything. So the first thing we want to do is have some fun with them. So basically we can say, okay, so what do they look like? Where can we find them? How many are there? And a priori, there doesn't seem to be that much rigidity to the way we have to study them. So we can sort of try to look for counterexamples in whichever way seems more natural. So today, instead of looking into sort of deeper stuff, so the way that the talk is scheduled, so will it involve microlocal analysis? No. Hyperbolic spaces? No. Heat? No. But crazy constructions? Yes. So in order to study critical points, most of what people have done so far is look for the worst possible thing, and then if it involves some crazy construction, then so be it. Yes. So first question that we have is, so we said that broadly, the bigger the eigenvalue, the more it oscillates, but can we have a very high eigenvalue on some manifold in terms of the index, but a low number of critical points? And it turns out that yes, you can. And so the counterexample was given by Dima Jacobson and Nikolai Nadirashvili in 1999. So what they do is that they look at the two torus and they say, okay, so if we have just sines and cosines, or maybe just sine x, the critical points are kind of like strips like this. Now, if you add some x to some, let's say sine x to sine y, the critical lines sort of tilt like this. And if you tilt them enough, you have just one continuous looping critical set. And if you perturb the metric, instead of having one critical set that is constant, you can sort of create some maximum and some minimum, but along this line. And so you break this critical strip into just finitely many points. So you have like a maximum here, minimum there, maximum here, minimum there. And it turns out that their construction, they can prove that you only get at most 16 of them. And you have an infinite sequence of such eigenfunctions. So you take the metric, add a conformal factor, get these nice properties, and show that you break this critical strip into sort of like just a bunch of maximum, minimum, and there's not so many of them. So that's the first construction. And until recently, there was not much more that we knew. But there was a sort of a big bang of critical points happening recently. So can we find a manifold M such that you have a finite eigenvalue and you have a lot of critical points? And the idea is a categorical yes. So you look at the two torus and you say, okay, so can I create infinitely many for a finite eigenvalue? Turns out that not only can you do that, but for the same metric, you have infinitely many of them. So basically, even if you have, let's say, one pathological case, you could maybe ask, okay, so what happens asymptotically with the lim inf? So what's the sort of like, or the lim sup as n tends to infinity? And I will sketch out the construction of what they did. But basically it says, if you're trying to look for an upper bound generally on manifold, it's going to be, you're going to have to work for your meal, because there is this such a pathological example that basically trying to find universal bounds is really impossible. Kind of like the way that this very specific example for very few critical points said, you can have as high as you want the eigenvalue, there's only 16 critical points. And here you can have infinitely many of them, infinitely often. So kind of like if you're trying to find upper bounds, you may have to look somewhere else. So same as Nadirashvili and Jacobson, they look at some conformal, a conformal deformation of the flat square metric on the torus. So here's the idea. So you say, okay, we have these this decomposition into eigenfunctions in X and in Y only. So you separate variables. And you say, okay, so I'm going to try to find out what the eigenfunctions in X look like. And I'm going to try to make these oscillate as much as I can. Because cosine my has, it has points where the derivative is 0. And then since we only modify in X, we're going to get critical points everywhere we have derivative in X equals 0. So you have this equation. So phi double prime equal lambda q minus m squared. So the idea is that if when you study Sturm-Liouville equations and Sturm-Liouville problems, we always assume that the weight function, so you have let's say f prime prime plus qf equals 0. We always assume q to be positive. And then we have Sturm's theorem that says it only have like a certain number of zeros. But it doesn't tell you much about what happens when this weight goes from positive to negative. So the idea is that we're going to want to make lambda q minus m squared oscillate a lot. So we start with an eigenfunction and we say, okay, so if at one point it's equal to 1 and the derivative is 0. So we're going to start with a critical point and we're going to say, okay, whatever happens left of xm is irrelevant, but we're only going to sort of work on it on the right hand side. So we're going to say if lambda q minus m squared equals 0, great. So we have phi is 1, phi prime is 0, phi prime prime is 0. So good. So we have a critical point that's sort of like, it's going to enable us to have something which is very flat, and then we're going to make it oscillate. So if you have to the right of xm, you have a bunch of points, and then this weight, lambda q minus m squared, oscillates so fast that if you add one oscillation to the right, it cancels all the other oscillations to the left. So the weight goes like this. So it goes like every bump is bigger than all the other bumps combined. So you have this, this third inequality, and then you can say, well, safely, it's quite easy to construct functions like that. Like maybe, I don't know, like cos of 1 over x times e to the 1 over, let's say, x squared or something like that. So functions that sort of decrease really fast, but oscillate really fast as well. But they decrease faster than they oscillate. So the idea is that if you have something that oscillates in the way that I just written on point 3, then at between each of those points where the weight oscillates, it needs to change sign. So basically you create these critical points after that. Now, how do you do that rigorously is actually involves a lot of, let's say, sort of technical construction lemmas. So it's not deep mathematics, but it's just that you need to make sure that at every step your estimates are correct and that nothing sort of blows up on you. But let's say the extra thing that is nice about this construction is that when you want to say add one eigenvalue that has infinitely many critical points next to one point. So when you add this perturbation, you sort of move the spectrum. But if you have a very small perturbation, you don't move the spectrum by too much. So because you've got a lot of freedom to modify the metric left and right, if you keep enough freedom the way you perturb it, you'll have, let's say, enough freedom to force the eigenvalue to fit where you want it to be. So you fix, let's say, lambda km such that lambda q of xm minus m squared equals 0. And then you have these oscillations to the right. So the idea is that if you add smaller and smaller perturbations, and then you have this sequence of let's say, you take the metric, you add this flat part, you make it oscillate, you keep going, and then you add a flat part, you make it oscillate, you keep going. At some point, when you do that, you use Brouwer's fixed point theorem to show that it's always possible for m points, let's say 1 to m, to work. And then you show that at every step, the perturbation that you add moves the spectrum less and less and less. And so you can use sort of a diagonal argument to show that you can find an infinite sequence. So that, let's say the sort of more technical aspect is constructing your perturbations in a way that you keep enough freedom to make Brouwer's fixed point theorem work, but work really well so that you can go infinitely many instead of just a fixed number. So that's the idea. So remember this. So we start with the function. We say, okay, if at one point we have a phi equals to 1, phi prime equals to 0, then we can sort of keep going to the right the way we want to. We just construct some metric, which is sort of has period half the length of the torus. So we know that there's always dimension 2 in the eigenspace, and then we play with the eigenspace, and then we always get something that we want. But the idea is that we play with the metric to obtain the eigenfunction that oscillates the way we want. Now there is the converse idea. So if we have such a pathological example where we have infinitely many times that the metric sort of oscillates really fast, can we have metrics where we can give an absolute beautiful bound on depending on n? The idea is yes. The answer is yes. And if you look on the detours, but with the flat metric, so this metric is very analytic, and eigenfunctions are just sines and cosines. We can bound the number of isolated critical points, if they are isolated, by some power of n. And the power depends only on d. So I don't think it was written anywhere, but I checked the details this week. But the idea is that when you have trigonometric polynomials, so cos of n theta or sine n theta, you can use Chebyshev polynomials to bring it back to polynomials in sine theta and cos theta. So when you map, Tn to R2n, and then you take x1 and then you go cos x1 sine x1. So the idea is that if you have a polynomial in R2, so that when you restrict it to the circle, you always have, you can have any trigonometric polynomial, then you can use Moore's theory on polynomials, which we can then bound the number of critical points. So the idea is that Chebyshev polynomials in R2, when you restrict them to the circle, give you exactly sine n theta, cos n theta. So, so what you do is that you say, okay, I take my torus n-dimensional, put it in R2, and then instead of using sine on the circle, I'm just going to take this big polynomial that lives in R2, and then I'm going to take, you know, products of them like you would on a torus. So it gives you polynomials in 2n variables. And then you want to say, okay, so when is the gradient equals to 0 on the torus? So you use this very classical theorem by Milner that says if you have a algebraic variety, so you have whatever amount of polynomial equations, and then you say they're all bounded by degree d, and the sum of the Betti numbers of V in check cohomology is less or equal than d to the power m times some constant, and the constant isn't so interesting. The idea is that so check cohomology is sort of like is meant to deal with pathological spaces in a different way than singular homology and cohomology, but in terms of algebraic variety, it was shown sort of back in, I think, the 40s or 50s that every algebraic variety can be triangulated by some CW complex, and then you have this equivalence between cohomology and singular homology. check cohomology and singular cohomology. So basically it tells you that the number of connected components of the critical set is less or equal to d to the power m times a constant. So these polynomial equations, basically you have x1 plus x2, x1 squared plus x2 squared is equal 1, and then you have n of them. And you have the n equations defined by gradient p equals 0. And so you have that you can bound the number of critical points in on the torus. Also, when you take derivatives in just on the torus itself, it gives you other trigonometric polynomials. So going from the eigenfunction to the gradient of the function still gives you a polynomial in R2n. So basically, if you have the flat metric, you can give an upper bound. But if you ask me, well, can I take any metric? Then you have no upper bound at all. You have infinitely many eigenfunctions with infinitely many critical points. Now, if you have the flat metric, you can give this bound. But what about if you're close to the flat metric? Well, the answer is no. And we gave a counterexample of that with Pierre Berard and Bernard Helffer last year. And there exists a sequence of metrics, Gn equals Qn times G0, where G0 is the flat square metric, such that there exists at least one eigenfunction with infinitely many critical points. And you can take the conformal factor Qn to be as close as you want to the flat metric. So, but really, I mean, there was some aspects of Buchowski, Logunov, and Sutton's construction that allowed them to do the same thing that we did, so to make it as close as they wanted to the flat metric. But what we did is actually quite interesting in itself, because rather than taking a metric, having the metric do what we want, then showing that the eigenfunction gets what we want. So what we did is that we said, okay, but what if we start with the eigenfunction that we want right away? We just say, we're going to force this guy to be an eigenfunction. And does it work? And it turns out that actually it works. So you say, okay, I have this conformal metric.
Philippe?
Yes?
Sorry to interrupt you. There's a question in the chat
Yeah.
from Misha Karpukin. He's asking, close in what sense?
Yes. So that is hard. Like, I'm not super versed in, let's say, the spaces of metric, and like, let's say the distance between two metrics is like, if you embed both of them in R k to some k, then what is the let's say the Hausdorff distance between them? Now, it's not even sure that, for example, we can embed our metrics in R3. Kind of like the flat torus can be embedded in R3, but it's not sure that ours can be sort of nicely put in there. But we can actually discuss this at the end. I think that the idea of distance between metrics is something that I'm not super good at. So we actually took care to not explicitly say the meaning of close. All we can say is that we conformally deform it by something which is very close to 1. So it should be close in some sense to the flat metric. Also, when you look at Qm, the factor Qm, it goes to 1 in various types of convergence. So, for example, it's not something that converges to 1 in L2, but has these bits where it goes, like it blows up. It tends to 1 in C0, C1. Actually, we might be able to prove that it converges in CK for any fixed K. But it seems to go nicely towards what we want. Is that enough?
Thank you.
All right. So when you're looking at surfaces, when you deform it by a conformal factor, it's actually quite simple. So you just divide the Laplacian by the conformal factor. Then again, we look at eigenfunctions that we separate variables. So we look at phi of x, cosine y. And then we say, okay, so if we want this guy, this f, to be an eigenfunction of Laplacian with this conformal metric, with a fixed eigenvalue, then you have this relationship between qm, m, y, and phi, which is given over there. So basically, if we want to show that this is an actual metric, then we need to show that taking the quotient, for example, stays smooth, that you have 1 over m squared times phi prime over phi is strictly less than 1. And then this metric will be very well defined. So the idea is that, okay, so we've got plenty of parameters to work with now. So now it's time to have some fun. So if I'm looking for an eigenfunction and it gives me this relationship between m, lambda, and phi, can I sort of create a nice conformal metric out of it? And it turns out that, well, yes. And actually, you don't need that much freedom. So our constructions are quite, they're quite rudimentary, and it seems that maybe you can get an infinite sequence if you worked with like enough freedom in your parameters. So you take literally m squared, and this, actually it's not the same phi, but it should be the same phi here. 1 over psi 1, and psi 1 is this guy. So basically we just, instead of looking at the eigenfunction, if you look at f of x, y, if you replace phi by 1, you just have cosine y, and it's a nice eigenfunction, eigenvalue m squared. But you're going to get that qm is exactly 1. Now, if you perturb this, the function y, and then you add oscillations, we already have the same situation that we had with the previous proof where you had a flat part and then you added oscillations. So really in this guy, you can just add them. And then I think we chose something like e to the 1 over x squared times cos of 1 over x squared, something like that. Like you have a lot of freedom to choose which oscillating function you add, and then you make sure that all the derivatives are bounded. And then if you take this guy and then you sort of make it as close as you want to 0, the perturbation, then you can show that the metric that you have is well defined at some point, and there's no sort of like 0 points in the conformal factor, and then you've already won. So this is kind of like a basic approach to how to create critical points. So instead of looking at a metric, does it give me the points that I want? You look at functions, and then you say, well, does it give me the metrics that I want? So what you might be interested in is that, okay, so the metrics that we had here are extremely non-analytic at the point where the critical points concentrate. And the same for the result with the infinite sequence. So you have just a lot of, let's say, a lot of freedom for things to go wrong. But what if you actually restrict yourself to only analytic metrics? Well, you can sort of get a result which is close, but no, like it doesn't give you a strong counterexample, but it gives you a fairly decent one. So if I give you any n, any big N, an integer, you can find a metric Gn on the torus such that one of the first 4 eigenfunctions has at least n critical points. So if you want to have sort of a universal upper bound for the nth eigenfunction, you can't. Now, asymptotically, maybe not. In the same way that you could maybe take, you can take sort of like a lot of counterexamples in, let's say, just R2 with flat domains, but you have like sort of a dumbbell that sort of goes like this. So it keeps going like this, and then you have as many of them as you want. But in the end, it's not sure that asymptotically, like it doesn't see the global shape as much as the local one. So it's not sure that you have this asymptotic upper bound, which is as bad as with smooth metrics. But for any fixed n, we can sort of like give a counterexample that we can bound it universally, regardless of the metric. So it's the same idea as the last theorem. So we add analytic oscillations, and then we show that the metric that we get is well defined. And then we also know that the metric that we get can be, the conformal factor can be taken close to 1. So far, all the things that we've done were on torus, because it's also very sort of easy to separate variables. So all the examples that we had were basically one-dimensional. So we say, okay, so we're going to only perturb it in one direction. And you have points which already have derivative equals 0 in the y direction. So if I take this this point and I sort of get more points to the right, then all of them will still be critical points. Now, what happens when you don't have exactly the same structure? So if you're in a different conformal class, maybe. Well, the idea is that you can still do that, but it requires, let's say, one extra step. Now, when you had a pure separation of variables, you had a point where you could choose, let's say, the second derivative to be 0 in the x direction, first derivative 0, same in the y direction. But it didn't seem to, like all the eigenvalues sort of lived in the x direction, so lived in the y direction. So basically you have eigenfunction, which is eigenvalue lambda equals m squared, and then you have cos my. So basically all the eigenvalue is absorbed by the y direction, so you can sort of get it pretty flat on the x direction. But what happens when you don't? Like when you don't have a point which is already pretty, let's say, gives you a lot of freedom to work on this point already. So we constructed this counterexample on the sphere. So for, let's say, any small m, which is high enough, you have smooth functions. So the eigenfunction is going to be, phi. And the conformal factor will be the big G. And then the set phi greater than 1 has infinitely many connected components. So as a byproduct, you have infinitely local maxima. So you have infinitely many critical points. And we can sort of give bounds on the conformal factor Gm. So as m goes up, Gm looks like 1. So it looks like a rounder and rounder sphere, but it's actually, in our construction, we can show that at no point can it be arbitrarily close to the round sphere. So if you fix m, and then you look at Gm, you can't construct it in a way that Gm is arbitrarily close to 1, because that would mean that the whole eigenvalue gets eaten up in the, let's say, in the, let's see if theta phi, we look at functions of theta, and then in the phi direction, it doesn't absorb the whole eigenvalue. So you need to sort of pinch the sphere so that you make it absorb all the eigenvalue in the y direction. So either way, it's harder because you don't have points that already have your desired properties. So what we do is that we, instead of looking at a point that already does what we want, we're going to create that point out of any point, but we're going to choose, well, actually, we're going to choose it quite, let's say, non-scientifically. We're going to pick the most obvious one. So we're going to create this function. We're going to create the flat part. We're going to add oscillations. And then we're going to show that the metric that we get with the same relation that we had before is actually well-defined. So, so we're going to take this very specific eigenfunction, which is sine theta to the m cos m theta. It has eigenvalue m times m plus 1. But when you look at the cos, which is sort of like the vertical direction, it doesn't absorb the whole m plus 1. So you're going to always be left with something on the left-hand side. So that's why we can't sort of like get metrics that are arbitrarily close at every point, but we know that we can take m to be large enough, and then that metric will sort of like get rounder and rounder. So you start with this function. So it's the black curve on the left graph. And then we're going to flatten it around, around the maximum, which is pi over 2. And here's the idea. So instead of modifying the function on the whole the whole length of the torus, we're going to just perturb it in a small place, and then we're going to make it catch up to the original function. So basically, we only need to estimate what happens to the perturbed metric close to pi over 2, which gives you two additional problems. And then you need to show that the metric is well-defined close to pi over 2, and then it needs to also be well-defined at the part where you catch up to the original sine theta to the m. Now that's the, let's say, the fun part is that there are many ways that you can make it catch up. There are many ways that you can make it, actually no, there's only one way you can make it flat. It needs to be identically 1. But there's many sort of like ways you can do that. You can make it very small width and then catch up very quickly. You can make it small and catch up very slowly. You can make it quite big and then catch up sharply. Like there's many ways you can work with. So that's where the, let's say, the fun part comes in. And then you add on the flat part, you add this very oscillatory perturbation, and then you make it as small as you want, and then you're going to be fine. Now, to make the conformal factor bigger than 0 is really the, let's say, computationally hard part. Because at some point you need to estimate the second derivative of a thing divided by the thing. And then because you have a lot of freedom to play with, then you have a lot of parameters, and then you need to show that with all these parameters chosen sort of carefully, the metric is well-defined. And then if you want to make it sort of get closer to 1, you need to work even harder with those parameters. But it's just a long computation. I will not bother you with that. And required quite a bit of trial and error at first, because whatever seemed to work did not work. Need to play with it a little bit more carefully. But it actually, in the end, it works. So what does it tell you is that there may be a way to take an eigenfunction that has no critical, infinitely many critical points, perturb it in a way to create these critical points, and then show that the metric that gives you this eigenfunction is well-defined. Now, we did it on a torus, we did it on a sphere, but basically, these are two manifolds that you can sort of decompose eigenfunctions in two directions. So phi theta or xy, but what about anything? So that's a very sort of nice but not so nice open question, is that if you have any manifold, or you have a manifold, and you have one critical point, can you sort of perturb the eigenfunction around this critical point in a way that you can create infinitely many critical points, and then you don't change the metric too much? So it would basically say that for any conformal class, for example, there is no upper bound for the number of critical points for Fn. That really, if you're trying to bound the number of critical points, you need something super strong, like algebraic topology, Morse theory for polynomials, stuff like that. So it would either be your situation is super rigid and you have almost no space to play, or you have all the space in the world to perturb and add these oscillations everywhere we want. Now that's the first question. So is it super rigid, super flexible, or is there sort of a limbo in between? The second question is that, so we showed that for analytic, you can perturb the flat metric on the two torus analytically and then create arbitrarily many critical points for a fixed eigenfunction of eigenvalue less than the fourth eigenvalue. Now, does that is that true for the lim sup, for example? So do you get the same lim sup that we had for the flat torus if you have analytic metrics? Now that's not obvious, and I don't envision the methods that we use to be able to prove anything like that, but it could be a very interesting question. And the third open question is that when we wanted to perturb eigenfunctions to have infinitely many or just many oscillations, the metric had that many oscillations. So there's a way to quantify the number of oscillations of something. It's called the barcodes. So you take, let's say, if f, and then you want to look at the barcode of f, is that you take f minus 1 of minus infinity to a. So that's a set. And then every time you hit a critical point, the topology of that set changes. So it only changes at critical points. And then you have like points where the homology goes, let's say, bigger, then it goes back lower. Like, for example, if you had something which went like this, and then you go up, you hit many connected components, but when you keep going up, at some point, all of these connect back. But you can, whenever there's a point in a function where you start a change in homology and then that point stops, then you say that that's a bar. And then the amount of bars that you have when you consider the whole functions, because these bars were sort of open and close, and then you have many more as the factor a goes up. You can count the number of bars. So if you have a bound on the number of bars on the metric, you have a number of critical points that will be bounded on your manifold for a given eigenvalue. So that is a sort of another interesting question. Like, can you have a metric that doesn't oscillate too much, but it makes the functions oscillate a lot? So really, I think this is a field where a lot of people can sort of get their feet wet quite a bit because it doesn't involve a lot of very complicated tools. But the constructions that we get are quite, let's say, fun to think about and fun to play with. So I hope that I can have many fruitful conversations with people that did other constructions in the next couple of years. And I hope that this talk got you interested in the field as well. So thank you very much, and I'll finish here.
Thank you, Philippe, for this very nice talk. We are now ready for questions from the participants.
Yes.
So you could.
I have a question. If you can hear me.
Yes.
So suppose that you want to put a lower bound on the critical value. Like, suppose that you want the critical value, let's say, to be around square root of the the square root of the logarithm of the eigenvalue. That's the kind of where the maximum would generally occur. Are there any things known about, like, how many critical points there are above a certain level?
About like the number of critical points above a certain level or below a certain level?
Above.
Yes. So there's some results by Guillaume Roy-Fortin, I think with Guillaume Poliquin, so two former students of Joseph, that said essentially the sum of the maximum, if you cannot have more than a certain number of maximum above any given value, and that number decreases obviously with the value. But I can maybe find out that paper and send it to you as well. So this is for
Yeah,
maximum. I'm not sure about critical points. Like you could have maybe a lot of saddle points, but I'm not sure if you guys.
yeah, I guess I'm mostly interested in the local maxima. What paper are you thinking of?
Actually, I can. I think I have your email, so I can think about it. I can find it and send it to you after we're done.
You're talking about Guillaume Lafortin?
Yeah, I think so.
So he only published 3 papers, or unless it's a new one.
No, it's one of the ones that he did, I think, during his work with Joseph for his thesis. I think so.
No, actually, I think it's not Raffartan. So there
Is
was
it
a
Polynomials or Raffartan?
yeah. So basically, well, the first result in this direction, but it's somewhat different. It's about the number of nodal domains where a function takes a certain value. It was actually due to my brother Leonid and Misha Sodin.
That one I know.
Yeah, and then this was generalized by Guillaume Pélican to some setting. And then also there is a more recent paper which is joined with my brother and Vukash and Sorisavlevich, where we actually pursue this barcodes approach that Philippe has mentioned. And there we also have some results in that direction. So in particular, that there is only finitely many critical points above a certain value.
Did you estimate the number?
Yeah, I mean, there is a bound in 2 dimensions. I mean, our results are 2-dimensional.
Well, what kind of bound are you talking about?
Well, it's bounded. Well, let me see. It's easier. Well, you know, Steve, let's maybe discuss it. I mean, I don't want to take the time of everyone, so I can send you the paper and explain the result. That would be easier.
Okay.
Thank you, Yosif. Thank you, Steve, for the question. Thank you, Philippe. Are there any other questions or comments? Oh, there is a question in the chat from Muhammadun Gum on slide 19.
Okay.
He is asking that you want to hide QM and not QN, maybe in equation.
Oh
5.
yeah, I think I had QN at the bottom.
Okay,
Yeah,
so it's a typo, you would say.
Yeah, it's a typo.
Okay, and also he's asking, then must be non-negative. I think it's the same question. Yeah. Okay, thank you. Any other? Wait. There is a second question. In equation phi prime prime plus lambda qx minus m square phi equals 0. Well, then lambda qx minus my square must be non-negative. Is that
which one? Sorry, so that's.
Do you see the chat?
No, I cannot see the chat, but I can maybe try to open it.
It's on the same page.
1 minute. It's on group chat. Okay, so QN and not QM. Yeah. Lambda qx minus m squared be non-negative. Yeah, so basically, so you want the point at which you start. So when you start with the metric and you want that metric to oscillate, you want to make it oscillate after it hits 0. So you want lambda q minus m to oscillate, but at first you want it to be 0. Otherwise, you're going to have a function which starts going up like this, and then it starts to oscillate. So basically, you're going to get not critical points that are sort of like local maximum and minimum. You're going to get sort of just points where the derivative oscillates around something, but not 0.
Okay, thank you.
Thanks. Thank you.
Does anyone else have comments or questions? If not, let's thank Philippe again. Thank you, Philippe.
Yeah.
And I would like to thank everyone for attending the mini conference. I believe we are done with the conference. Yes, we are done with the conference. And I hope everyone enjoyed some of it. And I hope we will see all of you soon. The Spectral Geometry in the Cloud seminar will resume August 24 with a special event celebrating Dima Jacobson's 50th birthday. So there will be a few talks on that. The schedule is not up yet, but it will be there very soon. So I hope to see you all soon there. And then the usual seminar will resume on Mondays starting August 31st. Thank you very much.
All right, so have a nice day, everyone, and stay safe.
I will end the Zoom conference now. Bye-bye.
Thank you. Bye.
Bye-bye. Thank you all for attending.